We're looking at Chapter 3 of the Edexcel Year 2 Statistics and Mechanics course, the normal distribution, and this is our final chapter on statistics. So, this is how it works. If we imagine we've got some data that we're collecting, like the typical example I like to use is height. You have a lot of people that are an average height. So let's put average height here on our x-axis. And then if we go to the right, there are some people that are a bit taller than average. There's some people that are a lot taller than average, but not as many people. So if we look at it, it would go like something like this. The average would have a lot of people near there. And then it would come down like this. Okay, so lots and lots of people near average height. The further away you get from average, the lower the probability. So let's imagine the height of this is probability. That's a little bit of a fib, and we'll get into that in a bit, but essentially height can be probability. And then we do the same thing on this side, okay? Because there are some people that are smaller than average, some people that are a bit smaller than that, and then there's a few people who are very, very short. There's a few people that are very, very tall, okay? So close to average, you get a lot of data. So say in this region, we've got a lot of people, and then further away, you get less people, but it happens in a symmetrical way. Being a bit taller than average and being a bit smaller than average are just as likely as each other. Being very, very tall is just as likely as being very, very short. So we've got the average in the middle, and then it sort of spreads out. Now, it could be that if you look at a different population, you end up with a curve that looks more like this. You get it very, very spread out. We have the average in the middle, and it sort of very slowly does the probability goes down either side of it, or we could have a very steep one. We could have all the data sort of gathered up in the middle, and then very quickly it becomes very unlikely that you're far away from average. But what have we got here? We've got what we call a bell-shaped curve. It has this sort of flat bit, and then it gets steeper, rounds off at the top, and goes down symmetrically on the other side. It's bell-shaped, it's symmetrical, the highest bit's in the middle, and this is our normal distribution shape of curve, okay? Now, how can we link this with things that we've done before? So we know that this is where we're aiming, okay? Now let's go back and think about things that we've seen before. If we have a binomial distribution, so if we have a random variable which is binomially distributed with n and p, if you're not familiar with the binomial distribution, then it's in the first year of the course, and there is a video elsewhere on this site. If you look in the playlists and statistics for the first year, it's in there. We're looking at the binomial distribution. Now, if we say, let's say we've got a binomial distribution with 100 trials and p is 50. P is 50%, so 0.5, okay? So this you might recognize as I'm flipping a coin 100 times. How many heads would I expect, right? That's that experiment. So what you get would be something like this. The probability of getting 50 heads would be very, very high. The probability of getting 49 or 51 is going to be the same as each other. The probability of getting 48 and 52, are a little bit smaller. 50 is the most likely. 49 and 51 are still very likely. 48 and 52 are still pretty likely, and then it sort of tails off. So if we took that bar chart, which would have 100 different bars on it, or 101, sorry, we'd start at 0 and we go to 100, that you could have 0 heads, you could have 100 heads, but the chance of getting 0 heads is very, very small. The chance of getting 100 heads is very, very small. If we took that bar chart and we drew it all out and we put a dot in the middle of each one, and we join those up with a smooth curve, what we'd get, hopefully you can see the idea here, would be our normal distribution curve, right? It would look something like that. And in fact, later in this chapter, we are going to deal with approximating binomials to normal distributions. So that's the sort of idea, right? We're familiar with this from the binomial distribution. Now, what's the difference? Well, the binomial distribution is a discrete distribution. What's the outcome? Well, the outcome has to be 0 or 1 or 2 or 3 or 4 or 5 up to 100, okay? Those are the only outcomes that we can have for a binomial distribution. With the normal distribution, I've got a continuous distribution. I can be measuring something like height, okay? And now for measuring something like height, what we've done previously, and it illustrates this very nicely in the book, is we've grouped heights into classes, right? With a frequency table, a grouped frequency table. And so we've kind of been able to produce these bar charts, or in fact histograms if you think about it. Now, what if we don't want to do that? What if we actually want to represent the height of people as they really are, as continuous data? Then we end up with a smooth curve with our normal distribution smooth curve, okay? So a normal distribution is a smooth curve, it's symmetrical, the average is in the middle, and when I say the average, I mean average. Now previously we've used mean and median and mode. Well, the mean and the median and the mode for a normal distribution are all the same thing. We tend to call them, well, we always call them mu, and we tend to refer to them as the mean, but we always remember that the median and the mode are actually going to be the same value if we have a normal distribution. It's this bell-shaped curve. Now, this is where we come back and deal with the little fib I said about the height of this thing being the probability. And also it links to the idea that those three diagrams there were histograms rather than bar charts, because let's think about this. If this is continuous data on our x-axis here, if I pick a point on the x-axis, what's the probability of somebody being this height? What's the probability of us getting exactly this value here? Well, the probability of picking one specific number on a continuous scale is pretty impossible if you think about it. If I say what is the probability that somebody isn't just, I don't know, 182 centimeters tall, but 182.1357482 centimeters tall, okay? What's the probability of somebody being exactly that big and not a nanometer over, not a nanometer under? Well, it's once you put it in those terms, you can see that actually there's so many possibilities. The probability of anybody being any specific height is quite, is basically going to feel like zero, isn't it? So what we actually do instead is we don't do that sort of thing. We say, well, what's the probability of being somebody, if I'm interested in a value of 182, then what I do is I'd imagine a little band around it, and the area there is the probability. So the height of this thing isn't the probability, the area is the probability. So if I said 182, what I might mean would be 182 to the nearest centimetre. So what I really mean is, if I say what's the probability of being 182 centimetres tall, I'm asking the question, what's the probability that I'm between 181.5 and 182.5? And that, between those two lines there, that area gives us our probability, okay? So the height isn't the probability, the area is the probability, in the same way as on a histogram, the area is the probability. So on the vertical axis, which I've not drawn in so far, but on our y-axis is the probability density, okay? PD for probability density. Now, you will notice that we hardly ever bother with a y-axis on the diagrams that I'm about to draw, and in a lot of the diagrams in the textbook, they just look like this, with an x-axis and a curve. You'll also notice that I'm talking about this bell-shaped curve, and I'm talking about the area underneath it. So if you've never met this topic before, what you may be expecting is that in a minute I'm going to say, oh, so this is a bell-shaped curve, and the equation of this is y equals da-da-da-da in terms of x. Now, Google it, you can find that equation. There is an equation, there is a function, it's got e to the x's in it, which tells you the shape of the normal distribution, but we're not going to use it. We don't need to know exactly the function. It might be helpful to know that there is a function. Y is something in terms of x, and that function gives us this nice, beautiful bell shape, but we're not going to worry about that, and you'll see as we get through the chapter why we don't need to worry about that. So, what else have we to say? The area is the probability, so the total area underneath the curve has to be 1, doesn't it? Okay, the total area underneath the curve is 1. So if I did something like this, if I was interested in somebody being a height of less than 160 centimetres, so let's say this is 160 centimetres, the probability of somebody being less than that height would be this area here. So this area here is 1 take away this area here, okay? So if I split the curve up into two sections, this area plus this area makes a total of 1, because the total area underneath the whole curve has to be 1. And the total area underneath the whole curve has to be 1, just to spell it out, because if we do an experiment, if we measure something, one of the outcomes has to happen. If all of the outcomes are on the x-axis, then the probability of all of them has to be, one of them happening has to be 1. we also have, you'll notice in the textbook, if you look through the black bullet points here, they have this point, which is that they are, here it is, third point, the bell-shaped curve, and there are asymptotes at each end, here and here. Now, that's because our theoretical normal distribution has asymptotes. Our theoretical normal distribution has a mean here of mu, and then the further away you get from the mean, the lower the probability is. Let's go back to the practical example of height. If this is an average height here, well, there isn't an asymptote here practically. The function, the mathematical function, has asymptotes. As far as the mathematical function is concerned, it's theoretically possible for somebody to be, 5 meters tall. The probability of that happening is very, very small, and so that this line is getting closer and closer and closer to the x-axis. And by the time you get way over here to 5 meters, then the height of this thing is very, very small. So if I took a little tiny strip around 5 meters, it would be an incredibly small probability. As far as the theoretical probability is concerned, that is a possibility. Okay. But in practice, we know that it's not possible to be 5 meters tall. We know that there comes a point where you can't be past a certain height. There's the tallest person ever. If we're picking somebody out of the population, you're not going to be taller than the tallest person who's ever lived, and that person has a limited height. Okay, and same on the other side. You can't be a negative height. So this thing definitely can't be asymptotic. By the time we get to 0, this curve in real life would be touching the x-axis. But the function that we're dealing with is asymptotic, and it goes on forever in theory. Okay, we don't have to worry about that asymptotic nature of it to answer the questions. The only reason we do need to know it really is so we can draw the curve nicely, so it looks like these things are kind of asymptotic here. So what have we missed out? We have a mean. Just looking through the textbook now and looking at those points, those bullet points in bold there. We've talked about area under the curve being equal to 1. It's a bell-shaped curve with asymptotes at either end. It's symmetrical with the mean in the middle. So we have sigma squared, which is our variance. Okay. If we have a standard deviation of sigma, a bigger standard deviation would mean this thing is more spread out. So a normal distribution with a big standard deviation would look sort of flattened like that. And in fact, I've drawn these already, haven't I? So the one with the I've drawn that here now. This would be a big standard deviation. This would be a small standard deviation if all the data is bunched up in the middle. Okay. Now, points of inflection is another thing that's mentioned in those bullet points. Not something, again, that we use practically, but something we should be aware of to get used to the shape of this curve and the feel for it. Now, a different definition to the point of inflection that we've met in the core books. In the core books, we talked about points of inflection and first derivative equaling 0, that sort of thing. The way to think of it here is the point of inflection is where the gradient goes from increasing to decreasing. Okay, so the gradient here is positive and it's getting bigger. The gradient here is positive and it's getting smaller. Okay, it's not where the function goes from increasing to decreasing. So the function is increasing, it's increasing, it's increasing, and then after this point it's decreasing. Okay, that's the function going from increasing to decreasing. It's where the gradient goes from increasing to decreasing. So here the gradient is increasing, it's getting steeper, and then somewhere around here it's getting shallower again. Okay, and then obviously the opposite is true as well. So here the gradient is getting steeper but negative, and then getting less steep. So we have another point of inflection somewhere here. And they're useful because if mu is here in the middle, 1 sigma away from mu is your point of inflection. So that point there and that point there are within sigma of mu. Okay, so you're within 1 standard deviation of the mean. And there are 3 figures that are really helpful. Now, these are really, I think, a good addition. They didn't used to be on the A-level syllabus pre-2017. You could do this without having these figures in your head. And it's really helpful to get an idea for how far away from the mean you can be and roughly where you'd expect to be on the distribution curve. So what we have is that 68% of the data lies within 1 standard deviation of the mean. So what we're saying is, let's put in these facts together. From this sketch, the point of inflection looks to me about there. That's where the gradient stops getting steeper and starts getting smaller. And then the other one looks like it's there. So if this is mu in the middle, 68% is the area here. Okay? This is 1 sigma, so that this point here, I suppose, is mu minus sigma, and this point here is mu plus sigma. Okay? So if I tell you that I have a population, let's say cars on a motorway are driving at an average of 67 miles an hour, so that's 67 miles an hour, and there is a standard deviation of 4 miles an hour, then that would be 71 and that would be 63. Okay, so you've got some people here, you've got most people, 68% of people are going between 63 and 71. You've got some people going quite slowly, you've got some people going fast, and too fast in fact for the speed limit, but 68% are within this bit in the middle here. Okay, now because this thing is symmetrical, we can also use that information as 34% between 63 and 67 and 34% between 67 and 71. And also because it's symmetrical, we can use this fact that if this is 67, if that's the mean, if that's our mu, well, up to that is 50%. Because this is symmetrical, the whole area is 1, so 50% here, 50% up here. The area of this is 0.5, the area of this is 0.5. So if I want to go 1 standard deviation above the mean, then that is 34% in here. So those two areas altogether make 84%. Okay, so if you're looking at a normal distribution curve, whether it's a skinny steep one in the middle or a sort of leveled out flat one, you can look at roughly where the points of inflection look to be, and you can think about the area. This area should be 68%, the area less than, in this case, 71, so a mu plus 1 standard deviation needs to total 84, that sort of thing, okay? The next 2 bits of information are, so that the first one, 68% live within 1 standard deviation, 95% of the data lives within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean. So we can solve similar questions like this one. You know, if we had the question, the mean is 67, the standard deviation is 4, what's the probability of being less than 71? Then you could say, well, that is mean plus a standard deviation, so that's 34% there, 50% there. You can do similar things. If I instead of saying 1 standard deviation away from the mean, if I said 2 standard deviations away from the mean, you could use those percentages in the same sort of way. And we can do that, and in fact, that is the summary of exercise 3A, right? That's what they're asking us to do in exercise 3A. But what's more important than that is that we get a feel for the shape of this, right? So it's about 2/3 of the data is within a standard deviation of the mean. So if you're looking at, I don't know, let's say you're looking at IQ score, right? You're worried about whether your IQ score is high or low. If you know the average IQ score, well, IQ score is going to be a normal distribution, right? So most people are average IQ, some people are above, some people are below, a few people are a long way above, a few people are a long way below, but it's kind of symmetrical. You get as many slightly cleverer than normal people as you do slightly less clever than normal. And I know there's problems with saying IQ is a measure of cleverness, but you know, roughly speaking, so a few people with a slightly higher IQ, a few people with a slightly lower IQ. And the further away from you get from the average, the less likely it is. So you're worried about your IQ. You say, I know what the average is. In fact, I think I'm right in saying that average IQ is always fixed at 100. So you say, well, I'm worried about my IQ. It's only 90. Is that normal? Well, if you know the standard deviation is 20, then you know you're well within this 2/3 of people. Okay, so that if the standard deviation is 20, then 68% of people have an IQ between 80 and 120. By the way, I have no idea whether that's a reasonable standard deviation on IQ scores. I don't know enough about IQ scores. If you are within 2 standard deviations, then you're within 95% of the data, right? So most people will live within 2 standard deviations of the mean. If you're outside of that, you're pretty unusual. You're in 5% of the data. So, and remember that 5% is split into some up in the sort of high extreme and some down in the low extreme. So one of those extremes might be a positive thing, one of those might be a negative thing. More often, maybe both of them are negative. So let's take the example of high IQ. If you're further than 2 standard deviations away from the mean, you're 5% of the population. But if you are 2 standard deviations above the mean, you're in only 2.5% of the population. Now, if that's IQ, good for you. You're very, very good at IQ tests, so you're probably very, very clever. If it's down here, then that's perhaps bad news. Maybe you're getting such a low score on a IQ test that maybe there's some concern there. But it could be, let's say it's something like weight. If you are in the top 2.5% of weight or the bottom 2.5% of weight, both of those are undesirable, right? Well, you're probably ill either way. Either you're obese or you are unhealthily thin. So there's no value judgment within the normal distribution. If you're a long way over to the left or a long way over to the right, you have to put the thing in context. Sometimes one's positive, one's negative. Sometimes they're both negative. Sometimes I suppose it could be neutral. Sometimes they might both be positive. I'm struggling off the top of my head to think of an example where being a long way away from average is positive in both directions. But if you can think of one, then well, let me know. 3 standard deviations, well, 99.7. For practical purposes, let's kind of call that 100%, shall we? Right. So basically, everybody's within 3 standard deviations. I mean, if you're outside of those 3 standard deviations, then perhaps we're not interested statistically. If we're doing things with statistics, we might be interested in identifying that group as to the people that are real outliers. But perhaps more often than not in statistics, we're looking at what do most people do? What's the usual response? What's the usual piece of data? So if you're outside of 99.7% of the data, perhaps that's less interesting to us. Okay, so that's the idea with the normal distribution. Let's just do a quick example. There's a little bit of notation that we need to get used to, and then a bit of a technique for how the questions work. So here's our notation. X is distributed with the normal distribution, mu and sigma squared. Okay, now as they've done in example 1 here, we've got X is distributed normally with 8 and 0.2 squared. Often we'll put that in like this. So we can see the standard deviation is 0.2. If we wanted to know the variance, we'd have to do 0.2 squared and work it out for ourselves. So often we'll put it in like that, just to tell us straight away our standard deviation. But they could easily give you an example where, in fact, I'm sure we can find one if we just look for a second, where, here we go, in question 4, X is distributed normally with a mean of 120 and a standard deviation of 16, a variance of 16, so a standard deviation of 4, okay? So in this case, X is distributed with a normal distribution, the mean is 8 and the variance is 0.2 squared, the standard deviation is 4. So if you want to know the probability that this random variable takes a value greater than 8, so, well, what's the probability of getting us a value bigger than 8? Well, here's 8, here is our mean. Probability bigger than that is this bit, the total area under the curve is 1, the area under this part of the curve has to be 0.5 then, or 50%. What's the probability of getting a value between 7.8 and 8.2? Well, that cunningly is 1 standard deviation away from the mean. So within 1 standard deviation of the mean, it's going to be 68%. How do we know that? Because it's one of the 3 numbers that we memorize: 68%, 95%, and 99.7%. Okay. You'll find in exercise 3A that all the numbers that you're dealing with, you can get at as 1 or 2 or 3 standard deviations away from the mean. Watch out for that situation where they are asking you for this position. They're saying what's the probability of being less than 71, so that's the 50% plus half of 68% and variance on that. Okay, so that's section 3.1. Have fun with exercise 3A.